Okay, let's take a look at problem 2 now. Okay, so here's problem 2. We are given two companies, S and D. So company D produces furniture and it gains the profit PI for furniture number I. And there is also a company S that produces components necessary to build those furnitures, and the cost of buying component I from company S is CI. So this is pretty much the setting of the project selection problem that you saw in class. Also, there are dependencies. So for example, in order to build furniture 1, you might need to have components 1, 2, and 10. So we have dependencies of this sort for our problem. Now, so in the original problem, what you were doing is you wanted to identify a set of furnitures and therefore a set of components such that the sum of the profit that you make out of those furniture minus the cost that you need to pay for the components is maximized, which we then showed that it is equivalent to minimizing the sum of prices of furniture that you're not going to build plus the cost of the components that you're going to need. And then we used a network to find the mean cut there, which would then again be equivalent to finding that minimum. But what's different in this problem is that we don't really have these prices CI. So basically, assume you are this company S's boss and you want to specify appropriate prices such that your profit would be maximized. So again, company D is going to select a set which would maximize its own profit. But the thing is, if you set these prices too high, you will, summation of these prices is going to be high for you. But then in that case, company D is not going to buy many components from you because it's not going to make any profit. So you should set these prices such that you maximize your profit, but also that company D would buy this from you, right? So the objective that we have here is pretty much the same because company D is going to maximize its profit. So we want to specify this price as CI such that, company D also maximizes its profits. So a little bit of, so if you, we name C as the set of components that we have and F as the set of furniture, and C of X, by C of X we mean the components that you need if you want to build furnitures of X when X is a subset of F. Okay, so basically you are going to specify some set X here, and then you will need to pay for components in C of X. Now, this is the setting, this is the network that we used for the previous problem when we had both PI and CI and we just wanted to specify which furniture we would decide to make, which projects we would decide to do. So what we did was we set these edges as having capacity PI, these edges as having capacity CI, and for the edges in between we specify capacities infinity. And what happened is, like, when you select a subset of these furniture to make and therefore a subset of these components to buy, what will happen is that you will be paying. So if you consider this value you will be basically paying this PI. So the value of the cut is going to be these PIs for furniture which are not amongst those you chose. And then from this side, you're going to pay for CI for those components which you do need. And in between, there will be no edge. And that's because you found a you found a mean cut. And in a mean cut, all the edges have to be with full capacity. And well, if they are with full capacity, then the value of your mean cut would have to be infinity because the capacity of these are infinity. But we know that we have at least one cut with like limited value, and that's when you just set S aside and the rest of them aside, the value would be sigma of pi. So that's not going to happen here. And so basically in your cut, you will not have any flow going from part of this part of the graph to part of this part of the graph. Because if it does, then it has to go to full capacity, and that's infinity, but we know that we have a cut of finite value. So this is how that problem went, but here we don't have these values ci. We want to specify them. So basically we are having two objectives here. We are facing two objectives. First of all, we would want to maximize our own profit, but the underlying problem is that the problem D, company D also wants to maximize its profit. So we should also consider that. So what we're going to do here is we're going to set these capacities as infinity. Okay, so we don't have these CIs, but we're going to set them as infinity, and then we're going to solve a max flow problem in this graph. And that will give us a flow F, and so some flow is going to go through all these edges here, and we are going to set the price of that component, that according component, based on whatever value, whatever flow goes through that edge. So this is how we're going to price. Now it is left to prove that this is going to actually give us a optimal pricing, meaning that there is no other pricing possible that would give us more profit, given that company D is also maximizing its profit. Okay, so let's first take a look at what will happen here when we find a max flow in this graph. So have in mind that these edges here and the edges here all have capacity infinity. So the only thing that is limiting us in finding the max flow is just these capacities here. So what we can do is that we can go with full capacity through all of these edges, and then the flow will somehow move on to T. So these edges are going to be full when we find the max flow. Now what we do here is that we then set the prices as the flows that go on here, right? Now consider for once again that once we found those values which we named CI, consider that graph with these capacities as PI, these capacities as infinity, and the capacities here as CI. Now note that in this graph, the max flow is going to be equal to the sigma of all these prices here, okay? Because, so if we find a max flow in this graph, we are not going to find a flow more, because if we could find a flow more, then we would have been able to find it in the graph before, where the capacities were infinity. So the flow that we'll find in this new graph with these prices is going to be the same flow as we did before, and that flow we claim that is equal to the sigma of prices here and also the sigma of prices here. So the sigma of profit here or the sigma of profit here. And the reason is that, well, if you consider the cut S and everything else and then T on the other side, you will see that all of the edges going from everything else to T, which is just these edges, are at full capacity. And that would mean that we have a cut, and the value of this cut is exactly equal to the max flow, and so it's a mean cut. So basically, if it was possible that there was another set of pricing, C star, that would give us more profit, then, so assume that we have this price as C star, which would give us more profit when solving this max flow problem here, then have in mind that the flow that we already found is equal to the sigma of these prices here, and no flow in this whole network can be anything more than this, because, well, the max flow's value cannot be more than the summation of the capacities going out of S in any graph. So what we have here with these prices C1 to Cn is the max flow is equal to the sigma of profits here and is equal to the sigma of these CIs here. Now, if we can set some other prices here, the flow that we're going to find in this new graph cannot be more than the sigma of pi. If you have another set of prices here, and then you find the max flow, what you will be getting paid as is like, so if this is the mean cut in the new network with these prices, then you will be getting paid, like company S is going to be paid the sigma of all of these edges, flow of these edges going from this part to T. So what they will get paid is part of the sigma of these C stars, okay? And now have in mind that when you find the max flow, the value of the max flow is going to be always something less than or equal to the summation of capacities here going out of S and the summation of capacities going to T. So even if you consider all of the summation of these C stars here, that's going to have to be like the flow that would go through them in that case would have to be less than or equal to the summation pi here. And basically the money, so the profit that we're going to make with these prices C star is going to be less than or equal to the sigma of C star here, and is equal to the flow that goes from this part to T, which we can name as C star, and that value is definitely less than or equal to this sigma pi here, okay? So, well, if C star is the optimal pricing, that's the setting that we would have. Now, let's take a look at the prices that we found. So we said that we set these prices as exactly the value. So when you find the max flow in this graph with these CIs, all of these edges are going to be filled up. And that would mean, and we said that, well, because all of these capacities were infinity at the beginning, then that would mean that all the capacity going out of S is also going to be filled up. So basically we would have that sigma pi here, which is, again, as I said, the maximum profit that we could possibly make in any case with any pricing. That is going to be exactly equal to the summation Ci here, and the profit that we'll be making is exactly equal to the summation CI, not anything less than that, because we said that these edges are all filled up in that case. So basically with these prices CI, we are making exactly the maximum profit that we can possibly make. So it cannot be that there is any other pricing that would give us more profit than that, because it cannot be more than the sigma pi, and we are already gaining that sigma pi. So this pricing is going to be optimal, and it's going to give us the maximum profit. And that's how the proof of this problem goes.